Welcome to the Holographic Universe. This is part 2 of a 5-part workshop series designed to examine how quantum physics and recent scientific experiments are radically changing our understanding of life, our reality, and our spirituality. Let's briefly review what we learned in part 1. First, matter is not solid. It is mostly empty space.
We were all taught in school that the world is made of stuff, of matter, of mass, of atoms. Atoms make up molecules, molecules make up materials, and everything is made of that. But atoms actually are mostly empty. For example, if this ball were the nucleus of an atom, a proton in a hydrogen atom, for example, then the electron circling this, which would describe the outer limits of that atom, would be out by that mountain over there, roughly 20 miles away. And everything in between is empty. In fact, the universe is mostly empty.
Remember Dr. William Tiller saying, "Within all the atoms and molecules, all the space within them, the particles take up an insignificant amount of the volume of an atom." We also learned through the double-slit experiment that these particles that make up matter are not particles all the time. They are waves until they are observed, and then they pop into being a particle in a specific location. In fact, these particles are actually waves most of the time.
The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like waves. Physicists were completely baffled by this, so they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of 2 bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. It was here that physicists stepped forever into the strange, never world of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
We learned there is a field that exists as waves of possibilities and contains an infinite number of wave frequencies to create the physical universe that we see. This is where all particles live as waves until they are observed and pop into a specific physical location.
And what we've discovered at the core basis of the universe, the foundation of the universe, is this single universal field of intelligence, so that all the forces of nature and all the so-called particles of nature are now understood to be just different ripples on a single ocean of existence. That's called the unified field or superstring field, a single universal field of intelligence, an ocean of existence at the basis of everything, mind and matter. And all the so-called particles of the universe, the forces in our universe, everything in the universe are just ripples on that ocean of existence. That's the unified field. And that field is a non-material field. Planets, trees, people, animals, we're all just waves of vibration of this underlying unified superstring field.
Physicists give this a name. They call it our quantum wave function because it seems wavy. However, this wave function isn't just a wave of matter like an ocean wave or a sound wave or any kind of wave of matter. It's a wave of possibility. It's a kind of thought wave. And because it is a wave of thought or possibility or not matter, it's invisible to us. But we can't explain what we do see as matter in these small corners of space and time unless we picture that these matter particles somehow come out from or emerge from these thought wave patterns which are invisible to us.
We also learned how a hologram is made using a two-step process. First, we shoot a laser beam out of a laser gun, and then we immediately split that laser beam into two beams. One of the beams, called the reference beam, makes its way and eventually hits a sensitive holographic plate or film. This is like the film we used to have in our cameras before digital photography. The other half of the laser beam hits an object first, in this case an apple, and then hits the holographic plate. When these two parts of the original laser beam come back together at the holographic plate, they interfere with each other just like the waves did in our double slit experiment, and they form an interference pattern on the holographic plate. If you look at the holographic plate at this point, you cannot see the apple. All you can see is the interference pattern, which looks like a bunch of waves. So at the end of step 1, we have an object stored on the holographic film in wave frequencies. To get that object to pop out as a hologram, we now need to do step 2 by focusing another laser beam on the holographic plate where our apple sits in wave form, and if we get just the right angle, out pops the apple, looking very real and very solid. What we didn't talk about in part 1 was that a single piece of holographic film, or plate or disc, can store a very large number of objects on it. In fact, a hologram is such an efficient storage device that it is the next step in computer storage. Very soon you will begin to see what's being called a holographic versatile disk, or HVD, which can store 30 times the amount of data as a DVD. So, to make one certain object pop out as a hologram, like our apple, the laser in step 2 has to choose those precise wave frequencies for the apple by being shot at a specific angle at the film. In part 1, we learned that the physical universe we see is actually not solid matter at all, but more like a hologram.
But surprising new clues are emerging that everything, you and I and even space itself, may actually be a kind of hologram. That is, everything we see and experience, everything we call our familiar three-dimensional reality, may be a projection of information that's stored on a thin, distant, two-dimensional surface. Sort of the way the information for this hologram is stored on this thin piece of plastic.
Is the three-dimensional world an illusion in the same sense that a hologram is an illusion? Perhaps. I'm inclined to think yes, that the three-dimensional world is a kind of illusion, and that the ultimate precise reality is the two-dimensional reality at the surface of the universe.
When we look at some of the modern scientific views of reality that have tried to get down to the nitty-gritty, we see that at its ultimate level, say in M theory or string theory, that reality is not solid, it's mostly empty space, and whatever solidity it has seems more to resemble a hologram picture rather than material, harsh, solid reality.
In short, quantum physics says that the physical universe we perceive as reality is created by collapsing the wave function from unlimited possibilities in the field into a hologram. But the holographic reality we see looks very real to us, even though it isn't real at all. Creating the illusion that things are located where they are not is the quintessential feature of a hologram. This is because a hologram is a virtual image, an image that appears to be where it is not. It is relatively easy to understand this idea of holism in something that is external to us, like an apple in a hologram. What makes this difficult is that we are not looking at the hologram, we are part of the hologram. So says Michael Talbot in his book, The Holographic Universe. The conclusion to Part 1 was that quantum physics is very clear. What we call reality is actually a holographic picture that only looks and feels real to us inside it. In the words of Albert Einstein, reality is merely an illusion, albeit a very persistent one.
The easy answer to the question as to whether reality itself is illusory and it's really all fuzzy, and it's all just probabilities, the easy answer to that would be yes. So, if I were hurrying off to a meeting instead of being interviewed and somebody came up to me and pestered me on the street and asked that question, and I'd say, yes, that's basically right. But it's more complicated than that, because it's only fuzzy when you're not interacting with it.
Whether or not we're just living in a big holodeck or not, it's a question that we don't necessarily have a good answer to. I think this is a big philosophical problem that we have to deal with in terms of what science can say about our world, because we are always the observer in science. So we are still always constrained by what is ultimately coming into the human brain that allows us to see and perceive the things that we do. So it is conceivable that all of this really is just a great illusion that we have no way of really getting outside of to see what is really out there.
But this idea that reality is an illusion is not a new concept. Hinduism, Buddhism, and Sikhism all talk about Maya, or life as an illusion. Mipam Rinpoche said that the real sky is knowing that samsara, the physical world, is merely an illusory display. The Kabbalah says that the first aspect of God is all that there really exists. All else is an illusion. And A Course in Miracles puts it this way: in any state apart from heaven, life is illusion. Outside of heaven, only the conflict of illusion stands, senseless, impossible, and beyond all reason. Illusions are but forms, their content is never true. What quantum physics has done is first scientifically confirmed what many other people have said about reality being an illusion, and secondly, discovered what reality actually is: a holographic picture that only looks and feels real to those inside it. You could actually call this physical reality we live in a holographic 3D total immersion movie. Here's Woody Allen's version of a total immersion movie. And let me set this up for you. The man you will see wearing a jungle hat was a character in a movie, but he stepped out of the movie and escaped into the real world and met a woman and fell in love. Now he wants to take her back into the movie with him.
Look, I don't want to talk anymore about what's real and what's illusion. Life's too short to spend time thinking about life. Let's just live it.
Live it how?
Well, we'll begin with dinner.
Oh, listen, no, we can't. I've only got a few dollars.
Well, we're not going to use your money.
But that's all we have, unless you've done something.
Well, say no more. The moon will be full, the stars will be out, and we're going stepping.
But we're broke.
Leave that to me.
It's him! Tom, you're back!
I want you to meet my fiancée, Cecilia. Oh, well, you know all these people.
It's not possible.
I'm in the world of the possible.
Yeah? Well, you better get back in the store, you little weasel.
Ah, you anticipate me. Follow me.
Saints preserve us.
Trust me.
He just comes and goes like he pleases.
Come on.
But she can't be in here.
Why not? Come on.
Cecilia, my money's good up here. Got too much money. But it upsets the balance.
What's the difference? He's back, isn't he?
I told you he'd be back.
Can we get on with the plot now?
I'll can we with her here?
But she's here with me, and I'll sock any man in the jaw who makes her feel unwanted.
Well, it's about time you got back
Right,
here.
now we finally go to the Copacabana. None of us have eaten in ages.
Good. I'm bringing a guest.
Won't Kitty Haynes be surprised? Table for 7, please, Arturo.
Yes, sir. 7.
7.
That's impossible. It's always 6.
We have an extra.
7, Arturo.
This person.
So let's not speak of love sublime, because time brings on a breakup. There'll be no tears and no emotional scenes to spoil my makeup. And when the end comes, I'll take up the slack.
Would you like some more champagne?
Oh, thank you.
Until
Listen,
you
Tom, I don't know what they're charging you, but those champagne bottles are filled with ginger ale.
That's the movies, kid.
I don't care. I love every minute of it.
Domesticating every Sunday, Monday, one day at a time. Let's take it one day at a time. Let's take it one day.
Who are you? Oh, no, I came with Tom. You sing so beautifully.
What the hell is this? We're supposed to meet and marry. Who's the skirt?
My fiance.
Oh, what? No, wait.
He met her in New Jersey.
What is this?
Kitty, she's real.
Kitty!
Quick, Paul Ginger.
Which brings us to the question, exactly how is this holographic 3D total immersion movie created for us to experience as physical reality? Just in the last couple of years, we have discovered the answer to that question through some very amazing brain research. Dr. Karl Pribram has had a long and illustrious career. Born in Austria in 1919, Pribram is both a neurosurgeon and a neurophysiologist who spent many years trying to find out where memories are stored in the brain. The problem was that in the 1920s, the brain scientist by the name of Carl Lashley had found that no matter what portion of a rat's brain he removed, he was unable to eradicate its memory of how to perform complex tasks it had learned prior to surgery. So Pribram set out to solve the mystery of memory storage that seemed independent of brain cells, called neurons. But it wasn't until Pribram met David Bohm, one of the pioneers in quantum physics, that he found his answer. Here's how Michael Talbot describes it in his book, The Holographic Universe. Bohm helped establish the foundation for Pribram's theory that the brain operates in a manner similar to a hologram, in accordance with quantum mathematical principles and the characteristics of wave patterns. Technically, Talbot continues, Pribram believes memories are encoded not in neurons or small groupings of neurons, but in patterns of nerve impulses that crisscross the entire brain in the same way that patterns of laser light interference crisscross the entire area of a piece of film containing a holographic image. In other words, Pribram believes the brain is itself a hologram. Just as a hologram functions as a sort of lens, a translating device able to convert an apparently meaningless blur of frequencies into a coherent image, Pribram believes the brain also comprises a lens and uses holographic principles to mathematically convert the frequencies it receives through the senses into the inner world of our perceptions. In short, Pribram believes our brains mathematically construct hard reality by relying on input from a frequency domain. That's a very important sentence you will hear several times. Our brains mathematically construct hard reality by relying on input from a frequency domain. Let's translate all of this into simple English. According to Carl Pribram and the results of many scientific experiments, some of which we will discuss in a minute, the human brain itself is a hologram. Its function is to receive holographic wave frequencies from a frequency domain, what we are calling the field, and translate them into the particular physical universe we see out there. Particular meaning made of particles in this case. Again, from Pribram, our brains mathematically construct hard reality by relying on input from a frequency domain. Or, our brains construct our holographic physical reality after receiving and based on wave frequencies from the field. You may have heard of another famous physicist, Nikola Tesla, who also said, "My brain is only a receiver." In the universe, there is a core from which we obtain knowledge, strength, inspiration. I have not penetrated into the secrets of this core, but I know that it exists. Think about a radio or TV set, which convert wave frequencies we cannot see into sounds we can hear and images we can see. Many scientific experiments have now proven that, in the same way, the human brain receives wave frequencies downloaded to it from the field and then converts those wave frequencies into our holographic physical reality. We're going to take a look at some of those scientific experiments and watch and listen to some of the experts involved.
Scientific experiments have shown that if we take a person and hook their brains up to certain PET scans or computer technology and ask them to look at a certain object, and they watch certain areas of the brain light up, and then they've asked them to close their eyes and now imagine that same object. And when they imagine that same object, it produced the same areas of the brain to light up as if they were actually visually looking at it. So it caused scientists to back up and ask this question. So who sees then? Does the brain see? Or do the eyes see? And what is reality? Is reality what we're seeing with our brain? Or is reality what we're seeing with our eyes?
Next, Dr. Stuart Hameroff from the University of Arizona is going to describe a very famous experiment done by Dr. Benjamin Libet in the late 1970s.
In the late 1970s, a neurophysiologist at University of California, San Francisco, named Ben Libet did some very famous experiments. What Libet did was study patients who were having neurosurgery on their brains, with their brains exposed, while they were awake. They were given a local anesthetic to numb the area of the skull and scalp to access their brains. And they were awake, and Ben would talk to these people. So, for example, what he did was he would stimulate their little finger and look at the part of the sensory cortex on the opposite side that was related to that, record from it electrically, and ask the patient when he or she felt the stimulus on the little finger. And he would also stimulate at that particular area of cortex.
Let me make sure you understand the setup. A patient was on the operating table, fully awake, but with their skull and scalp anesthetized and the skull cut away so that their brain is exposed. Dr. Libet would stimulate their little finger on one hand, maybe a pinprick or needle stick, and the patient was supposed to tell Libet as soon as they felt the stimulus. Then Libet would directly stimulate the part of the brain associated with that same little finger and ask the patient when they felt that.
Now, what you would think would be that if you stimulate the little finger, it takes a finite period of time to get to the opposite side of the cortex, so the patient would report it a fraction of a second later after the stimulus. And when you stimulate it directly, the patient would report it immediately. He found just the opposite. When you stimulated the little finger the patient felt it immediately, and when he stimulated directly in the cortex, there was a delay.
The brain is actually where we feel things. So when you stick the little finger with a needle, that sensation has to travel to the brain before it is felt. But if you stimulate the brain directly, you should feel the stick immediately in your little finger because the sensation is already in the brain. But, contrary to all expectations and logic, the patients felt the needle stick on their little fingers immediately, and it took time before they felt the stimulus directly to the brain. Libet was flabbergasted. He tried to find an explanation, as did many other scientists, and the prevailing theory became that time can travel backwards. It's called the time reversal theory, or subjective backward referral, or antedating. However, after trying to prove this and failing, Libet himself later said there appeared to be no neural mechanism that could be viewed as directly mediating or accounting for the subjective sensory referrals backward in time. In other words, there is no evidence in the brain for time reversal as the explanation for this phenomenon. Just put that information to the side for a moment, and let's go on to the next experiment.
So the experiment that I developed to look at this is we wire you up typically to look at skin conductance, but also heart rate and other parameters. You will sit in front of a computer screen and you press a button, and you know that 5 seconds later you're going to see a picture. It could be a very calm picture, or it might be a very emotional picture. And it's randomly selected by the computer immediately before it's shown. So when you press the button, the future is not yet determined. So you need real precognition in order to be able to jump into the future and get it somehow. So since we're looking at your physiology, we know what happens to physiology after you see an emotional image, and we know what happens after you see a calm image. The question is, does that future experience leak into your present? Does it happen before you see the picture? And through this experiment, you can see what happens. Electrical activity of the heart, EKG. This is photoplethysmograph, which is the amount of blood in the fingertip, and respiration, breathing in, breathing out. Press the button, well, what happens to physiology? Well, if it starts rising before the image appears, it may suggest that you're about to get an emotional picture. And if it stays calm, it suggests maybe you're going to get a calm picture. So we've done this kind of experiment for several hundred people, and colleagues have run this experiment as well, and as it turns out, that is exactly what you see. People become aroused before randomly selected pictures in the future that happen to be emotional, and they remain calm before randomly selected pictures that are calm. This has been seen in heart rate changes, in skin conductance, in the brain, and basically systemically throughout the body.
The only conclusion to this experiment that makes any sense is that the brain knows what picture the computer is going to choose and display before the person is aware of it. Indeed, before the computer has even chosen which picture to display, and the body is responding accordingly. Basically, what science is discovering is that our brains seem to know what's going to happen before we do.
There have been some studies which have shown that when people are beginning to move a hand or beginning to say something, that there's actually activity in the brain in certain nerve cells of the brain, even before they become consciously aware of what they're trying to do.
That's worth repeating. There have been some studies that have shown that when people are beginning to move a hand or beginning to say something, that there's actually activity in the brain or certain nerve cells of the brain even before they become consciously aware of what they were trying to do. As strange as that may sound, it is being proven time and time again with the latest research and technology. Here is a BBC documentary from June 2010 that confirms this phenomenon. What our experiments reveal is that there is a deterministic mechanism unfolding that leads up to your decision at a later point in time. Remember what Carl Pribram said, that our brains mathematically construct hard reality by relying on input from a frequency domain. If we put these brain experiments together with Pribram and what we know from quantum physics, the conclusion is inescapable. Your brain first receives a hologram in wave frequencies downloaded from the field. It then translates those waves into particles to create your holographic physical reality, and then it sends that reality out there for you to perceive and experience. You remember how a hologram is made. At the end of step 1, we have an object stored on the holographic film in wave frequencies. To get that object to pop out as a hologram, we need to do step 2. Therefore, here's what we're talking about in terms of the human brain and our holographic universe. If we consider that the field is like one giant, actually infinite, piece of holographic film with every possibility already contained in it, in other words, step 1 of creating the hologram has already been done, then what Pribram is talking about is a new step 2 to get our holographic reality to pop out, where wave frequencies are downloaded from the field to the human brain, translated into particles, and then projected out there to appear as our holographic physical reality. Or, as Pribram actually said it, our brains mathematically construct hard reality by relying on input from a frequency domain. So let's talk about each of the brain experiments we looked at.
In the late 1970s, a neurophysiologist at University of California, San Francisco, named Ben Libet, did some very famous experiments.
In the Libet experiments, when he stimulated the little finger, it took no time for the sensation to be felt in the brain because the brain already knew the little finger was going to be stimulated, since that hologram had already been downloaded, translated into a hologram, and projected out. But when the brain was stimulated directly, it was like a new hologram being downloaded to the brain, so it took time to send the sensation out to the little finger and back to the brain again.
So the experiment that I developed to look at this is we wire you up. Typically,
in Dean Radin's experiments, the brain knew what picture the computer was going to choose and display because it was all part of a hologram that had already been downloaded, translated into a hologram, and projected out. And as the brain sent that hologram out there to be perceived and experienced, the body responded to the hologram on its way out while it was being projected, so the body knew what picture the computer was going to choose before the computer actually chose the picture and displayed it.
In this region, there's
The only conclusion that makes sense when you put all these experiments together is that wave frequencies are being downloaded to the brain from the field, which are then translated into a particular or particle hologram and projected out there to perceive and experience as reality. And only when we perceive and begin interacting with that particular hologram do we become consciously aware of what's happening. And the whole process can take as much as 6 seconds. Let's briefly review what we talked about in part 1 of this workshop about an observer collapsing the wave function. We said that when quanta, or electrons, are viewed by an observer, these waves of possibilities pop and assume a specific location in space and time, which is what we see as reality. This is called collapsing the wave function. To put it the other way around, the natural state of an electron is as a wave. It only pops out of its wave state to form a particle in a specific location in space and time when it is being observed. This new brain research proves that the human brain is the observer that collapses the wave function, since quantum physics says it is the observer that changes an electron from a wave into a particle. Put more simply, it's the brain that takes those wavy 3D pictures and translates them into something we can see and understand.
Only conscious beings can be observers, then we're intimately hooked into the very existence of reality. Without us, there would just be this expanding superposition of possibilities with nothing definite ever actually happening.
Out of millions and millions of blobs of energy and light, photons and electrons, they make up this imaginary three-dimensional solid world, which doesn't exist at all according to relativity or quantum mechanics.
It might be easier to understand all of this by using an example we are familiar with: the personal computer. Computers use what is called binary code, which is made up of nothing but zeros and ones. If you look at the zeros and ones themselves, they look random and chaotic, like those wavy 3D pictures. But inside every computer is a CPU, a central processing unit, that acts as the brain of the computer. This CPU receives the binary code in sequences of zeros and ones, translates that binary code, and projects the results onto a computer screen where we can see it in a form that makes sense to us. For example, we start with binary code. In fact, that's what's happening right now in order for me to be able to show you this movie. A computer also has its own sensory perceptions, which include things like a mouse, a touch screen, a microphone, a video camera, and so on. When we interact with the computer through one of its senses, like clicking the mouse, that message gets sent back to the CPU for further processing. Therefore, in the same way that a computer's CPU receives the binary code, translates it, projects the results onto a screen, and then processes the inputs that come back through the mouse and other sensory perceptions, our human brain receives wave frequencies from the field, translates them into particles by collapsing the wave function, projects the results out there, and then processes the inputs that come back through our own sensory perceptions. And it all looks like this. This is a very important point. Our senses, seeing, hearing, tasting, smelling, touching, for example, are not really sensing some independent reality out there, but in fact are first projecting that reality so that it appears to be out there. It's not just a one-way street of incoming perception, but a two-way street of projection first and then perception. Apparently, once our brain converts the wave frequencies downloaded from the field by collapsing the wave function, it projects the results out there and makes it appear that we are surrounded by a holographic 3D total immersion movie. Once again, as Pribram said, our brains mathematically construct hard reality by relying on input from a frequency domain. Then and only then, our senses read what has been projected out there and bring that information back to the brain. Here's a video from YouTube produced by a Turkish non-scientist, Adnan Akhtar, that has a very good message but was a very poor English translation. So I rewrote and re-recorded the translation, and that's why it will be my voice that you hear.
We've been taught that the process of seeing is when light clusters, called photons, travel from an object to the eye and pass through the eye where they are refracted and focused on the retina at the back of the eye. Here, these light rays are turned into electrical signals and then transmitted by neurons to the center of vision at the back of the brain. We now know that the opposite is true, that the act of seeing actually takes place in this center in the brain. All the images we view in our lives and all the events we experience are actually experienced in this tiny and dark place. Both the film you are now watching and the boundless landscape you see when you gaze at the horizon actually fit into this place of a few cubic centimeters. These physical facts make us come to an indisputable conclusion. Everything we see, touch, hear, and perceive as matter is only electrical signals in our brain. For instance, we see a bird in the external world. In reality, this bird is not in the external world, but in our brain. The bird we see is in fact the electrical signals in our brain. Likewise, the sounds we hear from the bird are also in our brain. Put simply, the shape and sound of the bird are nothing but the brain's interpretation of electrical signals. This is also true when it comes to distance. Someone who watches the stars in the sky assumes they are millions of light years away from him. Yet the stars are actually inside him, in the center of vision of his brain. While you are watching this film, the truth is that you are not inside the room that you assume yourself to be. On the contrary, the room is inside you. When you see your body, you think you are inside of it. But remember that your body is an image formed inside your brain as well. To imagine matter to have an existence outside the mind is indeed a deception. The perceptions we observe may well be coming from an artificial source. We can understand this better with an example. Let's imagine that we could take our brain out of our body and keep it alive in a glass box. Then let's get a computer filled with information related to a particular setting, such as image, sound, and smell. We'll connect this computer to the brain with electrodes and send the pre-recorded data to the brain. As our brain receives these signals, it will see and live the setting that the computer is transmitting. We could also send signals to the brain from this computer about our own image. For example, we could send the electrical information, such as the sight, hearing, and touch, that we would experience while sitting at a desk. Our brain would perceive that we were a businessman sitting in his office. This imaginary world would continue as long as the information kept coming from the computer, and we would never realize that we were actually a brain sitting in a glass box. It is indeed very easy for us to be deceived into believing that what we are perceiving is real, even though it has no material basis.
We have been conditioned since birth to believe that what we see out there is real, an independent, objective reality that has a life of its own. And our role is limited to observing it and perceiving it and interacting with it. Not so, according to the latest scientific research. We are projecting our reality first and then perceiving it coming back to us. The bird first arrives in our brain as wave frequencies downloaded from the field. The brain then translates those wave frequencies into a hologram of the bird by collapsing the wave function. That hologram is then projected out there so that the bird appears to be real. And then the bird comes back to us through our physical perceptions.
The more you look at something in detail in what we think of as solid matter, the less and less solid it begins to look.
The only realities we know are the ones our brain manufactures. Our brain receives millions of signals every minute, and we organize them into holograms which we project outside ourselves and call reality.
It's as if you were sitting in the middle of a movie theater with a white screen 360 degrees all around you, but the movie projected onto that screen was coming from inside your own brain. In other words, although we don't know exactly how this works yet, your brain is the movie projector, and the movie you're watching, that you are totally immersed in, is a hologram and is not real. In 1991, before all this recent research took place, Michael Talbot asked, if the holographic brain model is taken to its logical conclusions, it opens the door on the possibility that objective reality, the world of coffee cups, mountain vistas, elm trees, and table lamps, might not even exist. Is it possible that what is out there is really a vast resonating symphony of waveforms, a frequency domain that is transformed into the world as we know it only after it enters our brain? Of course, now we know the answer is yes. That's exactly what's happening.
There is no out there, independent of what's going on in here.
Reality is unset jello. That's the way I like to put it. There's this just big indeterminate sledge out there that's our potential life, and there's and that we, by our very act of involvement, our act of noticing, our observation, we get that jello to set. We're intrinsic to the whole process of reality. Our involvement creates that reality, and so we have this involvement in everything. We are our world. There's no out there. We are, there's no place where we end and everything else begins.
David Bohm, you remember him, said that the tangible reality of our everyday lives is really a kind of illusion, like a holographic image. Underlying it is a deeper order of existence, a vast and more primary level of reality that gives birth to all the objects and appearances of our physical world in much the same way that a piece of holographic film gives birth to a hologram. Here are some more quotes from the holographic universe by Michael Talbot. For Pribram, this synthesis made him realize that the objective world does not exist, at least not in the way we are accustomed to believing. What is out there is a vast ocean of waves and frequencies. And reality looks concrete to us only because our brains are able to take this holographic blur and convert it into sticks and stones and other familiar objects that make up our world. If the concreteness of the world is but a secondary reality, and what is out there is actually a holographic blur of frequencies, and if the brain is also a hologram and only processes some of the frequencies out of this blur, what becomes of objective reality? Put quite simply, it ceases to exist. Although we may think we are physical beings moving through a physical world, this is an illusion. We are really receivers floating through a kaleidoscopic sea of frequency. Michael Talbot was clearly ahead of his time, because now we have proof that there is no out there. All there is a holographic 3D total immersion movie which we are projecting so that it appears to be out there. Now the interesting question comes, is there one big hologram of the universe that we all see and are all part of? Isn't that what is meant by the holographic universe? The answer is no. Each individual must have their own unique hologram they are projecting, their own private reality. Why? Remember the quote from Carl Pribram, who believes that the brain is itself a hologram which mathematically constructs hard reality by relying on input from a frequency domain. Since there is not one large common brain, there is also not one large common hologram. Each individual human brain receives and translates its own separate, individual, and uniquely downloaded hologram. If there were a common hologram, one big hologram of the universe for everyone, then we would each see reality exactly the same. And that doesn't happen. We all see reality just a little differently. For example, we're walking down the street and you suddenly stop and excitedly tell me, "Hey, that guy looks exactly like Brad Pitt." And I turn to you and say, "No, he doesn't. He doesn't look anything like Brad Pitt." What's happened here? You have seen pictures and movies of Brad Pitt, and you have an image of what you've seen. I could have seen those very same pictures and movies, but I have a different image of Brad Pitt. So when we see the same man on the street, he can look like your Brad Pitt to you, but he doesn't look like my Brad Pitt to me. If there were only one Brad Pitt that everyone saw in the same way, this kind of thing couldn't happen. But actually, we each see Brad Pitt a little differently. Or, we're leaving a restaurant and you say, "Can you believe how rude that waitress was?" And I reply, "I thought she was fine. She wasn't rude to me." Same thing applies. I perceive the waitress one way, and you perceive that same waitress in a different way, because we are experiencing the waitress in separate holograms. And we all know that 10 different people can have 10 different stories of how an accident happened. Now, these are small, minor examples, but our mental hospitals are full of people who see a very different reality than the rest of us, so different that they cannot handle it, and neither can society handle them. So each individual must have their own unique hologram they are projecting, their own private reality, especially since we each have an individual brain receiving our own personal holographic downloads. Besides, if there were one giant hologram we are all part of, it would mean there would be an independent, objective reality out there. And all the experts say that's not true.
There is no out there out there.
There's no out there out there.
There's an old New Age saying, "You create your own reality." While this is technically not true, what is true is that you are projecting your own unique holographic 3D experience that has been downloaded from the field to your brain. It's time to pull together everything we have learned in parts 1 and 2 of this workshop. We started with the double slit experiment, and we're going to end that way as well. Remember, physicist Richard Feynman has been quoted as saying that if you really understand the double slit experiment, you can understand all of quantum physics. So let's see what the double slit experiment says about the existence of an independent, objective reality out there. This time, listen to physicist Thomas Campbell from December of 2011. One quick note, Dr. Campbell is going to use the words diffraction pattern instead of interference pattern that we were using in part 1. Basically, they're the same thing.
This is a double slit experiment. It's a very famous experiment. This experiment has probably been done more times, more places, by more people than any other single experiment in the history of science. And it's because it gives such strange results that everybody wants to do it and see if it works like that for them. So this has been replicated over and over and over again, and whenever done properly, it always gives the same results. it tells us something very important about the nature of reality. Here's what happened, and I'll show you why it is such a famous experiment. Early on, we knew that waves, if you had a wave came to this thing, we have a barrier, a hole, a barrier, and a hole. That's called a slit. And it's two of them. There's a double slit. That's where the experiment comes from. That if a wave came here, some of the wave would go through this slit, some of the wave would go through that slit, and the distance from here to here is a little shorter than it is from here to here, right? We can see that. That's pretty obvious. If that difference in distance turns out to be like this, so the wave coming from the top hole and the bottom hole are shifted in distance one whole wavelength, then they both dip at the same time, they both crest at the same time, and you get a spot of light there. But if they happen to be just that difference in distance, where one gets to a peak just as the other one gets to a hump, you add them together, you get nothing. That's why you get nothing there. So what happens is you get this series of spots. It's called a diffraction pattern when you have waves going through the two slits. So they did this experiment with the double slit. They found a way to just fire one photon at a time at the slits, a particle. What they expected to see was this. What they saw was a diffraction pattern. Okay, now that was a surprise. They didn't expect that. So they said, well, there's something funny going on here at these slits. So these little red things are detectors. And they said, we're going to put detectors there at these slits, and we're going to see what's going on. And they did. They detected every time a photon went through this slit, this detectors would say, it went through the upper slit, or the detectors would say it went through the bottom slit. And whenever they did that, they got this pattern. So now the problem was, we take the detectors away, and you get this pattern. Then the idea was those detectors, they're doing something there. But they found out, and these are called quantum erasure experiments, they found out that you could take this data with these detectors, take all the data, detectors are working, it tells you exactly what slit each one goes through, but you don't look at this data, and you don't look at that data yet, you just take it. Now if you look at it, you'll get this. But if you don't look at it, and then you erase this information of which slit they went through, you get this again. You see? So obviously reality is not objective. That's the double slit experiment, and that's why this is such a big deal, because it shows that reality is not objective. There's something else going on here. That's what we want to talk about. Well, I will give you a little experiment that I'm going to make up. This is not an actual experiment, what I'm going to tell you. This is just a logical equivalent, so it's easy for you to follow and understand. Actual physics experiments are very complicated, and they're very hard to explain, but this is, like I say, a logical equivalent. Let's say that we take 102 of this experiment. In other words, we're going to measure what slit it goes through, and then we're going to keep track of what happens over here on the screen. And we're going to do that just 102 times. And we're going to take data for an hour, put that in the computer, take the data again for another hour, put that in. And what we'll do is the first one we'll take this data, put it in an envelope, call it detector data, experiment 1, and we'll take this, put it in another envelope, call it measurement screen data, experiment 1, put those two envelopes into a big envelope and call it experiment 1. You with me with that? So I got an envelope that says experiment 1, and I've got inside that I've got two envelopes. One of them says detector data for experiment 1, the other one says measurement screen. So I've got all my data in here. So that's just an easy way for us to keep them straight. So we're going to do that 102 times, and because we're doing this experiment, we always expect that as the result. So after we have 102 of them, we look at the first one we did, and we take this data out of the envelope, take that data out of the envelope, and this is exactly what we see, just what we expected. That's the experiment we're doing. And then we take the last one we did, and we do the same thing. We want to make sure that they're the same, right, on both ends. So we do that, and we get exactly this. We get the two spots of light here is what we get. So the first one and the last one are like that. We assume all the ones in the middle were like that because they were all just done together. All right, but now what this delayed quantum erasure means is that let's take the 100 envelopes that are left, right? We got rid of number 1, we got rid of the first one and the last one. Now we have 100 left out of the 102. We'll take those 100 and we'll shuffle them, we'll randomize them up. Then we'll deal them out into two piles of 50. Now, one pile of 50 we will look at them. We'll take the envelopes out and look at them, and every one of them, all 50 of them, will look just like this. We have the two spots here. Now the other 50, we'll take out the detector data of each one of the 50, put them in a pile, and set fire to them. We're going to burn them. We're going to destroy them. That's our eraser experiment. Okay? I'm making a very simple concept in the eraser experiment. We just burn them and destroy them. And no, they're not still readable in the ashes. We'll take the ashes and put them in water or something. No, don't complicate the experiment. We're just going to burn them. That's going to get rid of them, and they will be erased. And then we'll open up these envelopes, and every one of them will be a diffraction pattern. You see? That's what I mean by a delayed quantum erasure experiment. Every one of them will be. And you're thinking, how could that happen? You see, the experiment was done, let's say, a year ago before we took these envelopes out and sorted them. It doesn't matter. 10 years ago. The amount of time is irrelevant. In these experiments, they're actually done like 10 nanoseconds. But it doesn't matter. If you can do it in arrears, you can do it any amount of time. So that's why this is weird science. It looks like, depending on what you do with this data, you make this change from this output to that output, right? That's what it looks like. But that's just because you believe you live in an objective reality. You see, in a statistical probability reality, this is still indeterminate. It hasn't happened yet because you haven't looked. You see, you don't know what it is. In an objective reality, you know because you did this experiment, that's what it had to be. So you believe that's the way it is, and then you somehow magically changed it to this. Well, there's no magic involved. It's just that because this data hasn't been looked at, it doesn't really exist yet in this reality. Because we live in a probabilistic reality. I know you're thinking, that sounds impossible, but that's because you are ingrained from your culture with the concept of an objective reality. You believe that's the way it is, so when you see this or hear about it, it just doesn't make sense. Just like the world being around didn't make sense.
Let's make sure we all understand what Thomas Campbell just said. He said that we have to actually look at, to observe, the measurement data taken at the two slits in order to get a particle pattern as a result. If we don't look at the measurement data, if we erase that data without observing it, then we get what he called a diffraction pattern, which Captain Quantum called an interference pattern in Part 1. In other words, apparently, it's not the active measurement at the double slit that matters. The only thing that really matters is whether we look at the data we collected. If we look at the data, we get a particle pattern as the result. If we don't look at the data, we get an interference pattern that waves make, even though the data was collected. If there were some independent objective reality out there we all share, the result of the double-slit experiment would be the same all the time, regardless of whether someone looked at the data or not. What we have instead is a totally dependent, subjective holographic reality that is unique for each individual and based on their observation. In other words, what you are seeing right now, and every moment you are alive, without exception, is a holographic 3D total immersion movie written uniquely for you, downloaded to your brain, translated into the holograms you see, and projected out there for you to experience. Let me say that again. What you are seeing right now, and every moment you are alive, without exception, is a holographic 3D total immersion movie written uniquely for you, downloaded to your brain, translated into the holograms you see, and projected out there for you to experience. Listen to Dr. Amit Goswami very carefully one last time.
This is the only radical thinking that you need to do. But it is so radical, it's so difficult, because our tendency is that the world is already out there, independent of my experience. It is not. Quantum physics has been so clear about it.
If all of this is true, and the latest scientific research says it is, the question then arises, Who or what is choosing certain wave frequencies from the field and downloading them to a human brain to be converted into particles to become the reality we see and experience? Or, who or what is writing the script for the holographic 3D movie you are now and always immersed in? Who or what is the laser that chooses the holographic 3D total immersion movie to download to your brain for you to experience as your reality? We will answer that question in Part 3 of this workshop series, and I guarantee the answer will surprise you and shake your most fundamental beliefs, like discovering that the Earth is actually round. Meanwhile, your homework, what I want you to do in preparation to watch Part 3, is to watch the movie called The Truman Show with Jim Carrey, and practice seeing the world out there as a hologram that you are projecting rather than as an independent, objective reality that you are merely perceiving and interacting with. Once you have done your homework, please visit www.holographicuniverseworkshops.com for more information about continuing with Part 3 of this workshop series. In the meantime, you can download my free ebook, Butterflies Are Free to Fly, a new and radical approach to spiritual evolution, by visiting www.butterfliesfree.com.